Determining whether a function is even or odd really comes down to the symmetry of the graph of the function. Even functions are symmetric across the y-axis, and odd functions are symmetric through the origin. The best thing about determining whether a function is even or odd versus the symmetries of a graph of an equation is that in function notation, you can always plug this into the calculator, look at the graph itself and see if it has those symmetries. And from looking at the graph itself, you can determine whether it's even or odd. There are algebraic ways of testing whether a function is even or odd, and they're given in the definitions here. For an even function, it's a little bit easier. You look at the function evaluated at the opposite of x. If you get the same thing as f of x, then it is an even function. Another thing that you can tell algebraically with whether a function is even or odd, the powers of x for even functions are normally even. The test for an odd function, let's say g of x is an odd function, you take the opposite of the evaluation of the opposite of x, see if that's the same as the original. If it is, it's odd, and if it's not, it's not odd. Odd functions normally have odd powers of x, which is another algebraic way of telling whether a function is even or odd. So the first example here, f of x equals x squared plus 1 over x to the fourth. Just by looking at this, it looks like that the function will be even because the powers on x are both even powers. And this is true. So algebraically, if we plug in negative x into this equation, we get this. And if we simplify this, negative x squared is the same as x squared, plus 1 over negative x to the fourth is the same as x to the fourth. And this is the same as the original function. This is the same as this one. Because of that, this is an even function. One nice thing about determining even odd is that if you find that one is that it's even, or if it's odd, it can't be the other. So it saves a little bit of time if you guess correctly. Another way to do this, go to our calculators, press y equals, plug in x squared plus 1 divided by x to the fourth. I'll graph that. And it looks like you could fold it over the y-axis, and that would mean it's symmetric across the y-axis, which means it's even. So just another verification that this function is even. Okay, here, determine if g of x is even, odd, or neither. In this case, we have x to an odd power, okay, and then x to, I guess, a fractionally odd power, so in the denominator it's odd. So I would probably guess that this is going to be an odd function, but let's just double check. So we'll look at the opposite of g of negative x, and maybe I'll write this another way. Write this as the opposite of g of negative x. Okay, this is the same as negative 1 times, put in parentheses here, take negative x here, raise those to the same powers. There we go. And now we still have this -1 out here, times negative x to the third power is the same as negative x cubed. And we're subtracting the cube root of negative x. So we can think of this as -1 cube rooted and x cube rooted. It's usually a little easier just to think, since you're taking the cube root, that will give you a negative. So this is the same as just negative x to the 1/3. And we can simplify this a little bit. So this is negative x cubed plus x to the 1/3. Now distribute in that -1, that gives me x cubed minus x to the 1/3, which is exactly the original. And this was the test that it's odd, so this one is an odd function. That one is an odd function. We can also look at the graph of this one. So go to y equals, clear that out, x to the 3rd minus x to the 1/3. Graph this. If it's symmetric through the origin, which it looks like it is, goes through the origin there. And if we fold it over again, it would fall on top of itself. So that one is definitely odd.